Today we'll be taking a look at the atmosphere, attempting to understand its role in not only life on the planet, but how it is a factor of the development and change of landforms and landscapes over time. Our planet, as you know, is powered in a sense by the radiant energy that comes from the closest star, in this case our sun. Because of the curvature of the Earth, the energy at the top of the atmosphere is unevenly distributed. There are energy imbalances that exist between the equator and the poles. The equator experiences what could be considered energy surpluses, while the poles experience deficits. The annual pulse of seasonal change varies in terms of this distribution of energy across the globe. The Earth's atmosphere also acts as a filter in this process. It absorbs harmful radiation, charged particles, and space debris, disallowing them from reaching the surface. The varied levels of the atmosphere, which we will be discussing today, receive solar energy and solar debris at differing amounts or in differing amounts. The lower atmosphere, for example, experiences an unevenness in its receipt of energy. This unevenness, however, is part of the system, and it is part of the insurance that we have life and life sustained on the planet. The unevenness of energy receipt empowers the balance that we see between the atmosphere and the lithosphere. It gives rise to the global patterns of temperature and patterns of circulation with regard to wind and ocean currents. The electromagnetic spectrum and radiant energy become really important components in our understanding of how the atmosphere interacts with the rest of the planet and its natural systems. The essential solar input to life is electromagnetic energy, and this is expressed in various wavelengths. Solar radiation occupies just a portion of the electromagnetic spectrum. The radiant energy that is important to life travels at the speed of light to our planet. Now it's composed, as I said already, of differing wavelengths. The sun emits radiant energy composed of a variety of these, 8% of which is ultraviolet light, X-rays, gamma rays. 47% is the all-important visual light, and 45% is infrared heat energy. Now, due to the sun's high temperature, the sun has a surface temperature of over 11,000 degrees Fahrenheit, its wavelengths are very, very short. Wavelength, in this case, refers to the distance between 2 points on any successive wave of energy. The number of waves passing through a fixed point in a second is known as a frequency. So electromagnetic energy then travels in a wave motion, and we understand it in terms of how that wave is structured and how that wave action expresses itself over time. Now, as I said before, the atmosphere has an important role in filtering this energy that we receive from the sun. And it filters the energy as it is expressed really in two ways, in short waves and in long waves. Let's take a closer look at this. Most of the initial radiation that comes from the surface of the sun is expressed in shortwave format. A very important brand of shortwave electromagnetic radiation is visible light. As the Earth responds to the electromagnetic energy that it receives from the sun, it too produces energy, or it radiates energy in this case. The radiant energy that the Earth then, as a cool radiator, expresses back out into the solar system as a response to the sun is generally in the form of long wave electromagnetic radiation. The primary form of long wave electromagnetic radiation that the Earth respires, in a sense, back out into the solar system, really, again, in a very concentrated format, is infrared energy or heat energy. Now, when looking at what we receive from the sun and how we respond to it in terms of our earthly systems, we have to incorporate the atmosphere, because the atmosphere is what initially comes in contact with the shortwave electromagnetic radiation that we receive from the sun. It is also a major factor in the long-wave electromagnetic radiation that we respond back with, or that the Earth radiates. The region at the top of the atmosphere that we initially recognize as receiving solar energy exists approximately 300 miles above the Earth's surface. Referred to as the thermopause, it is the outermost boundary of the Earth's energy system, and it is really the outermost aspect of our atmosphere. Due to the Earth's distance from the sun, we receive only a portion of what the sun actually produces in terms of energy. In this case, the thermopause interacts with only 1/2 billionth of the sun's total energy output. The fraction of energy that reaches the Earth, this very small amount of what the sun actually produces, is referred to as insolation or solar intercept. Now, knowing the amount of insolation that is intercepted by the Earth is important to a variety of physical geographers, especially climatologists. The term solar constant is applied in this case to the measure of average insolation received at the thermopause when the Earth is at its average distance from the sun. And we know that there is a seasonal fluctuation in terms of this distance from the sun. The term perihelion is applied to that portion of the Earth's orbit when the Earth is closest to the sun. This is when the northern hemisphere experiences winter, usually around January 3rd. At that point, we are approximately 91 million miles away from the sun. The Earth is at aphelion, or the farthest position away from the sun, when the northern hemisphere is experiencing summer. That's right around July 4th. We're approximately 94 million miles away. So what is the atmosphere, and what is its role in all of this? Well, the Earth's atmosphere is a reservoir of gases that are accrued over time. The modern atmosphere is recognized by secular geographers to be the fourth in terms of this veil of gas that has encapsulated the Earth. They situate this atmospheric history as extending over nearly 5 billion years of time. This means that according to secular science, our atmosphere today has an ancient origin, and it is the sum of all exhalations and inhalations of life on the planet throughout time. What we can all agree upon, however, is that the atmosphere that we understand as existing today has an ancient origin. It is also the sum of all exhalations and inhalations of life on the planet since life existed. The Earth's atmosphere is a series of imperfectly shaped concentric shells or spheres that transition one into the next. Each of these spheres are bound or connected to the planet by gravity. The atmosphere itself exerts weight. It presses downward under the pull of gravity onto the planet, onto the surface of the planet. Air molecules create air pressure through their motion, size, and number. And this pressure is exerted on all surfaces that come into contact with that veil of air. This weight that is exerted on the surface of the planet and anything that is living on that surface is air pressure. This air pressure is currently pushing on you right now. It even exerts pressure from within your body, pushing outward. Ironically, without this outward pressure that is exerted from within you or any other object on the planet, that object, including yourself, would be crushed if that didn't exist, or if there wasn't that kind of balance between outward air pressure and the pressure within. The Earth's atmosphere exerts an average force of approximately 14.7 pounds per square inch. Gravity compresses air. It makes it denser near the Earth's surface. Of course, as you move further and further away from the center of the planet, the air, its consistency becomes thinner very rapidly. This relationship between location, gravitational forces, and the content of the air becomes very, very important as we start to look at where life exists within the atmosphere itself. So let's take a moment to slice this atmospheric table up, or this understanding of our atmosphere, up into parts. We'll take a look at the composition of the atmosphere, how it interacts with temperature, and how it functions. We'll use the chemical composition of the atmosphere as an initial criterion for the understanding of the atmosphere and how geographers divide it into a variety of regions. If we look at it in terms of atmospheric composition, we have two broad regions. The first is the heterosphere. This is the outermost atmosphere. It begins at approximately 50 miles from the surface of the planet and extends outward to the transition known as the exosphere. The exosphere is the outermost sphere that we relate to the atmosphere, but exists beyond its border, or beyond that 300-mile expression of altitude. The heterosphere, by definition, is composed of lightweight hydrogen and helium atoms. The heterosphere today is the location of where many of our spaceships will orbit the planet. It is also the location for the entire International Space Station as it orbits the planet. We call it the heterosphere because this region is not uniformly expressed in terms of its chemical composition. The gases composing it are not uniformly mixed. They occur in distinct layers, sorted by gravitational forces, according to their atomic weight or atomic mass. The lightest elements within the heterosphere, and those that are most common, hydrogen and helium, exist closest to the exosphere, or to the outer edge, while the heavier elements, which begin to include oxygen and nitrogen, they're not as prevalent, are found closer or at lower levels within the heterosphere. The next layer, which we are recognizing through the lens of composition, is the homosphere. This is a region that extends from approximately 50 miles above the Earth's surface to the surface of the planet. Increasingly, as one moves toward the surface through the homosphere, we see a blend of gases that is nearly uniform in its concentration. The only exception to this appears between 12 and 31 miles out from the surface, which is a region that contains ozone and the various expressions of water vapor and pollutants that are associated with our activities on the face of the planet. Now, the present gaseous proportions of the homosphere come to include things like oxygen, nitrogen, argon gas, carbon dioxide, neon, helium, methane, krypton, ozone, nitrous oxide, hydrogen, and xenon. It is believed that the concentrations of these fairly stable gases have evolved over the last 500 million years. One gas in particular, in this case carbon dioxide, is considered to be a natural byproduct of life processes on the planet. It is an essential, stable atmospheric component of the homosphere. Now, although its present percentage of composition is small, at slightly over 0.037% in terms of the overall content of the homosphere, it is important to our next criterion. So now we're going to slice up the atmosphere looking through the lens of atmospheric temperature. Our Earth has 4 distinct temperature zones, and one of these zones is the one that I used to introduce that outermost edge of the atmosphere, the thermosphere. The thermosphere is the heat sphere. It corresponds to that portion of the heterosphere, or that portion of the upper elements of our earthly atmosphere, existing between 50 and 300 miles above the mid-latitudes and the surfaces within them of the planet. When the sun becomes more active throughout our seasonal cycle, in terms of the production of solar radiation, this portion of the atmosphere will swell in size. It can become as high as or extend as far as 340 miles. As we move from the base of this initial sphere to the outermost edge, we recognize that temperatures rise. The intense solar radiation in this portion of the atmosphere excites molecules, individual molecules, primarily nitrogen and oxygen. They vibrate rapidly and produce a rise in temperature that can exceed 2000 degrees Fahrenheit. The next layer, just below the thermosphere, is the mesosphere. This is an area that exists between 30 and 50 miles in overall altitude. Its outermost boundary, the mesopause, is the coldest portion of the atmosphere, in this case averaging temperatures of 130 degrees below Fahrenheit. When we look back at our chemical composition criteria, we realize that this mesosphere is actually the highest portion of the homosphere. Now, the mesosphere is a very dynamic place. Sometimes it receives quite a bit of cosmic or meteoric dust, and this dust, these dust particles which get caught up in this element of the atmosphere, become nuclei around which fine ice crystals begin to form. These crystals seem to glow in moonlight, creating what geographers call noctilucent clouds. Below the mesosphere, in terms of our temperature criteria, we have the stratosphere. This section of temperature layers extends between 11 and 31 miles from the surface of the planet. Temperatures ironically increase with altitude in this layer, from below 70 degrees Fahrenheit to reaching 32 on average degrees Fahrenheit. Then finally below this, in terms of our look at temperature, we have the troposphere. This is the final temperature layer that solar radiation is encountered as it surges toward the surface of the planet. It is important because it is home to the biosphere, where we live, and it is the only location where weather occurs. Approximately 90% of the mass of the atmosphere and the bulk of all water vapor, including clouds and air pollution, are found within the troposphere. Its upper limit averages a temperature of below 70 degrees Fahrenheit, and then as we move down toward the surface of the planet, we start to see average temperatures which are important to our understanding of climatic regions. The temperatures expressed along the surface of the planet, again at the base or the kind of lower elevations of the troposphere, are known to be affected by things like elevation. They will also be impacted by the presence or absence of surface water. And of course, they will be impacted by the amount of living organisms concentrated within areas of that surface environment. The variations that we see expressed in terms of temperature in the lower troposphere can be categorized or understood through a look at two different kinds of rates of change. The rate of change, referred to as a normal lapse rate for the troposphere, is approximately 3.5 degrees Fahrenheit per 1,000 feet. Again, this would be feet that you are moving above or below the planet vertically. Another rate of change is recognized or referred to as an environmental lapse rate. This is the rate of change that makes more sense to us. It's the rate of change associated with specific times of the year or specific places. Temperatures will change in regions according to local patterns of weather and climate. Our final atmospheric criterion relates to how the atmosphere functions. In this case, we recognize two zones or regions in relation to function. These zones are important. They remove harmful types of solar radiation that are, in this case, integral to our survival. The first zone is the ionosphere. The ionosphere is the outermost layer of the atmosphere in terms of function, and it extends throughout the temperature area of the thermosphere and the mesosphere. The ionosphere absorbs cosmic rays, gamma rays, X-rays, and other short wavelength kinds of energy expressions, such as ultraviolet radiation. Given its chemical nature, it's also a location where we see atoms being changed into positively charged ions. The other region in this kind of functional criterion is the ozonosphere. The ozonosphere is that portion of the stratosphere, and again that's a temperature consideration, that contains an increased level of ozone. Ozone is a highly reactive oxygen molecule made up of 3 oxygen atoms instead of the usual 2. Ozone absorbs wavelengths of ultraviolet light and subsequently radiates this energy as long wavelengths rather, or long wave energy expressions, or infrared radiation back out into space. This process converts most harmful ultraviolet radiation, effectively filtering it and safeguarding life on the Earth's surface. So there you have it. That's the atmosphere. We can look at it through 3 different lenses, but we realize that it is integral to life as we know it on planet Earth. The criterion that we will focus most of our discussion in this course on is the temperature criterion. As you can imagine, when we're talking about weather and climate, the troposphere as a expression of atmospheric temperature and space becomes very, very important to us. And as you begin to look at climate maps and places within those climatic regions, you will want to consider the atmosphere in that region, both in terms of temperature and to a lesser extent in terms of its chemistry, to understand how life behaves in that region. In this case, the kinds of plants and animals that are now calling a climate region home. But we'll save that for another lecture.